Hey, how's everybody doing? Welcome back to the Math for Healthcare video lecture series. We're going to be looking at random variables and probability distributions. All right, I hope you're excited because this is really getting into the nut and bolts of probability and statistics. All of them use this idea of random variables and a probability distribution for those random variables. So we start with the random variable definition is a rule that assigns a number to each outcome of a chance experiment. For instance, a random variable may be the number of heads that come up when you're flipping a coin 10 times. That's an example of a random variable. More concretely here, we consider tossing a coin 3 times and observing the number of heads. We're going to let the random variable x denote the number of heads that occur in 3 tosses. I want you to think about this. What are the values x could take on here? We call that the range of x. Well, it could take on the value 0, right? You get 0 heads, you get 1 head, you get 2 heads, you can get 3 heads because you're tossing it 3 times. Now, remember this is our sample space, right? So here, you could think of this outcome, this is the value of x. So for instance, right, if we get 3 heads, obviously x is 3. If we get head on the first one, head on the second one, tail on the third, that's going to be a value of 2 because there are 2 heads. So on and so forth throughout, where all tails would be 0. If you need a minute, take pause and take a look at that. All right, so it's a value for each outcome. Now, like I said, the set 0, 1, 2, 3 is the range, and those are the values that x could take on. All right, so here, notice the value, when we say x equal to 2, that's an event. What event is that? That's this event, that, remember events are subsets of the sample space? That's the event x equal to 2, right? Because it's every place, every outcome where x is 2. So they really are events. It's just a nicer way to write down, and it works out quite well for us, and it's pretty critical. Okay, so here, the probability of x equal to 2, well, there's 3 of those, right, in that set, over 8. We've known how to find these probabilities. This is important to be able to understand what this means. Probability of x equal to 2 is the same thing as this set over here. Okay, likewise, we could write inequalities. So the event 0, x is greater than or equal to 0 and less than or equal to 1, that is this event here, right? That means it's when x is 0 or 1. Up here, that's looking at this group of them, 0 or 1 in this case. All right? And the probability of x greater than or equal to 0 and less than or equal to 1 is just 4/8. We just count those. Now, let's suppose we have an experiment where a coin tossed 3 times. We have the following sample space. Now, do you remember we're tossing a coin? When you said last time we're going to call this binomial, and we'd actually say it's a binomial random variable. But now let's say y is a random variable as the number of tails observed. Y would also be a. Which of the following events is the event y equal to 1? What is it? It's the number of tails. So when we have 1 tail. Oh yeah, looks like E to me, right? That's the event where we have 1 tail. Let's see a different kind that's not binomial. And here it's let the random variable y denote the number of coin tosses in the experiment, and basically until a head occurs. Well, now the values of y Well, the outcomes look like that, so the values of y, they keep on going. There's no stop to it. It keeps on going forever. We say that we don't have fixed trials, and that's what makes it not binomial. And we actually call this geometric. All right. And what's the probability y equal to 3? Well, think about it. We have to get a tails on the first, a tails on the second, and a head on the third. So that is going to be 1/2 times 1/2 times 1/2, or 1/8. Now, whenever we talk about a random variable, generally there's a lot of times we're interested in the whole probability distribution for that experiment or that random variable. Each outcome is assigned a probability between 0 and 1, inclusive, and the sum of the probabilities have to be 1. All right? And so we'll define the probability distribution of a random variable here. The values that x takes on are x1, x2, little x1, little x2, little xn, and so on. Then the probability distribution is, well, over here on the left, and sometimes I'll do this up and down. Maybe I'll write it down here to see. I'd probably write this something like x equal to xi, and the probability of x equal to xi, I mean the same thing. And we look at our values, x2, and so on. This is the probability of x equal to x1. All right. And they satisfy these conditions. All the probabilities have to be between 0 and 1. That shouldn't be surprising. And when we sum up all the probabilities, we get 1. All right? Let's see a couple of these here. Let's return to an example where we flip a coin 3 times. The random variable x is the number of heads observed. All right, so we want to come up with the probability distribution with this. Okay, this is... Notice those are all the x values that could take on. We could have 0, 1, 2, or 3 heads. Those are the probabilities, so I'll let you confirm those. Right. Just this note here. We have, if A is a set, P of A equals 1/8. But we really mean when we talk about a random variable, we need the P of x equal to 3, the probability of x equal to 3. Probability of x like that is meaningless. Okay, there's our probability distribution, and graphically, which is usually a histogram, at least for these discrete probabilities. And look, how do we read this is, well, think about this. The area of this first box is the probability that x equals 0. And we see this makes sense to us because the probability of success was 1/2, right? So that means that the figure that we look at here, it should be very symmetric, and this is the middle of it, right? Okay, and we would expect that because the probability of success is 1/2. And let's remind ourselves this is a binomial with n equal to 3. That's how many times I'm flipping the coin, and the probability of success is equal to 1/2. Well, why is it binomial? Well, it's a fixed number of trials, and we know that the trials are independent, right? Flip one coin, next coin is not affected by that. Okay, I'm gonna skip that there. So, if we want to find, looking at this, we want to find the probability that x greater than or equal to 1, less than or equal to 2, we simply sum those up, which, by the way, visually, what is that doing? 1 and 2. That's finding the area, this blue area there, which is 6/8 or 3/4. We've seen that. Does this following histogram depict a valid probability distribution for a random variable? Why or why not? Got to think about it. I pause. No, It doesn't. Why? Because when we sum them up, it's not equal to 1. 1/8 plus 4/8 plus 3/8 plus 3/8 is 11/8. That's it. That makes it not a valid probability distribution. That's an extremely important part of the probability distribution. Okay, suppose a pair of dice are rolled. Let x be the random variable that corresponds to the sum of the two numbers observed on the dice. So let's find that probability distribution. You could try it on your own. All right, we've done this. But what are the possible values of x? Well, they're from 2 to 12. All right, and what we call is this is pretty symmetric because the probability of getting a 2 is the same as probability of getting a 12. The middle one is 7. Probability of your sum 7. Remember that was the highest probability when 2 dice. And we could draw you could draw a histogram for this. I'm not going to take the time to do it, but this is another example of a probability distribution and a random variable. All right, so now let's see here. Binomial random variable. I'll give you a slide next, but what we've seen is this is fixed number of trials we need. And here, let's see, how many we're rolling? 3, a spare 6-sided die rolled 3 times. So my n is 3. Okay, that's the number of trials. And dice are independent trials, and we only have success and failure. And our probability of success here is it's a 2 or a 3, so that's going to be 2/6 or 1/3, which automatically means my probability of failure is 1 minus p or 2/3 here. All right. Now, what are the values x can take on? I'm just going to start building a probability distribution. It can be what? We could get 0, 2, or 3s. We could get 1, 2, or 3. We could get 2, 2, or 3s. Or we could get 3, 2, or 3s. Now we have to find these probabilities. All right. Now the formula for it's slightly complicated. Not too bad though. I'll probably do that in a separate video because it's not as important. We're going to use Desmos because we're going to say, I'm telling you right now, well, this is a binomial random variable. I need a distribution. So if I go over to my Desmos, all I simply do is say, oh, okay, I want binomial distribution. And now it tells me I need 3 trials and my probability of success is 1/3. What? Okay. So that's giving me, I could zoom in here. Wow, my zoom does not work well through my interactive chart. Okay, let me just resize this real quick. X-axis, we're going to go -1 to 6. Y-axis, we're going to go -0.5 to say 1. I know our probability is not going to be above that. Okay. What? Why isn't that showing up on my screen here? Damn. Okay. So let's see here. I'm having a little issue with Desmos. Interact. Okay. What is going on there? Well, let me fill in. I'll get you that in a second. It looks like I'm having a little too. I'm going to write down approximate numbers. Let's say 0.3 for the probability that I get 0, 2s, or 3s. Okay, not too surprising. But if I get 1, that looks like 0.44. Probability of getting 1, 2, or 3 is 0.44. Probability of getting 2, 2 or 3s is going to be 0.22. And here the third is going to be 0.04. All right? Now, that's our probability distribution form. It is in Desmos. You could type in, the command is binomial distribution 3 1/3. All right, try that out for other ones. Now, if we want to get a picture of what this looks like, I like GeoGebra for pictures. Okay. Yeah, 3 1/3. Okay, I got my picture up there. Let's do here we go. That's the picture of a probability distribution for binomial random variable x, where you're rolling 3 dice. So certainly we're not going to be able to go out past 3 here, all right? And this is the histogram we get, and this is how we visualize it. And certainly, since the probability is less than 1/2, we expect the bigger ones to be over to the left side there. And notice we can look at the heights to find our actual probabilities here if we wanted to. It's just easier to get on Desmos. Like I said, I don't know why that's giving me an issue here, but that's okay. All right, so that's our probability distribution. If you add them up, they'd be 1. And that is the probability for a binomial random variable. Oh, I see what happened here. Okay. Big Desmos, little Desmos. There we go. There is on Desmos for finding the probability distribution. Okay, notice the heights of those give us my probabilities of each of those values of the random variable. Here's this binomial distribution is how, DIST, sorry, that's how I enter it. Okay. Now, that's a binomial random variable. In general, what makes a binomial random variable? They're very important, very useful. Okay? So what they are is it's a binomial experiment, and the binomial random variable is going to be the number of successes in this experiment. What we need, the number of trials in the experiment is fixed. Okay, what was it in coins? That's the number of coins, or in dice, the number of dice we're rolling. That's the number of trials. That's how we check if it's fixed. You have to check these. It's important. It's very useful when we know it's binomial. There's 2 outcomes, success and failure. The trials are independent of each other. This is extremely important. So the probability of success is the same in each trial. All right, for dice, for the coins, we know this is the case. A single trial in a binomial experiment is called a Bernoulli trial. Less important. More important is fixed number of trials, 2 outcomes, and the trials are independent. 3 things that are that are really important for checking here. All right. And like I've written down, we usually use P for the probability of success, Q for the probability of failure, and Q is always going to, because there's only 2, Q is always equal to 1 minus P. Right. Now, this is close to the binomial distribution. Here we have 11 monitors, 3 of which are defective. Find the probability distribution for the number of defective monitors in a sample of 3. So let's say we say X equal number defective monitors and sample of 3. All right? Well, we want to come up with a probability distribution for that. Here, right, this is a bit more complicated. because, well, I want you to check, is this binomial? And explain why to yourself. Not binomial, since trials are not independent, right? Because why? Because if we pick out one and we pick out a defective model, the next time I go in there, the probability of getting defective is only going to be 2 out of 11 or 2 out of 10 instead of 3 out of 11. So the probability changes. Okay? That's a big thing. Not binomial because it's not independent. However, it's very related. In fact, let's take a view of what it looks like. All right, for in GeoGebra, that's the binomial that you see there. Oh, geez, I'm over here. That's the binomial that you see there. I want hypergeometric. Okay. And here it's a little different. The population size, well, I have 11 monitors. The number, well, we have, 3 defective ones, right? Notice getting a defective, we're actually kind of calling a success here. And we're pulling out 3 of them. Okay. Now, that's what I'm going to change this color right here. Color, come on, let's see here. Let's do something like blue. Okay, so the blue one is my hypergeometric. Let's look at that alone. The blue one is the hypergeometric. Okay, and now I'm going to overlay the binomial that's very similar. Well, not quite similar. Here's an idea of our. This is giving us basically our probability distribution. What is the, look at this, probability of getting 0 bad ones looks like about 0.35 or so. Probability of getting 1 bad monitor when you're selecting 3 is like 0.51. 2 looks like about 0.15 or 1.4. And 3 looks pretty small, almost 0. Now, how would we find it? Remember, we've done these problems in counting. If we had a count, all right, Desmos does not have, Desmos does not have a hypergeometric distribution in it. All right? So we kind of have to go do this by hand. First is, what do we got? What are our different x values and their probabilities? Okay, well, we could get 0, we could get 1, we could get 2, and we could get 3. And we all agree with that? Good. Okay. Now, find this probability distribution. Let's look at this guy. All right, star is going to be the probability that x equals 2. That's exactly what goes there. This is the good-bad problems when we did the counting and probability. So when we do the sample space, we count everything together. There's 11, and we're choosing 3. And then the numerator, we separate them. We have 3 bad ones. We want to know about getting 2 of them. And now we have how many good ones? That's 8 good ones, and we have 1 left to choose, right? Do we remember these types of problems? It looks, if I went back to GeoGebra, let's see, if I calculated this out, which is, let's see, I could do this in, it looks like that comes out to be somewhere about 0.14. Let's see, If I do it in, where's my Desmos? There we go. That's going to be 3 choose 2 is 3 times 8 choose 1 is 8. And then we're going to divide that by 11 choose 3. And it comes out to be 0.14545 repeated. So that's pretty close to what we got from our chart there. I'm going to put that in 0.145. All right, what I would like you to do is finish filling out this probability distribution. And we will use it in the next lectures when we get into expected value. All right, what do we have here is the probability that x is 0. Here's probability of x equal to 1. So on and so forth. All right, well, go ahead and try that out. Try some homework problems, and I will be back in the next video.